Our objective in this lesson is to illustrate joint variation. Let's have a quick review of our previous lessons. Tell whether the following is a direct variation, inverse variation, or neither of the two. Number one is a graph of an inverse variation. Number two, 40 times 1 is 40, 8 times 5 is 40, 4 times 10 is 40, 2 times 20 is 40. Since we have a constant product of x and y, then this is an inverse variation. Number 3 is an example of direct variation. Number 4, the hours of overtime you render and the amount of salary you get from it. The longer hours you work overtime, the higher the amount of salary you will receive. This is a direct variation. And last one, notice that we have three variables here. This is neither direct nor inverse variation. Today's discussion will focus on joint variation. This happens when one quantity varies directly with two or more other quantities. Let us recall our last example in the review part earlier. A is equal to length times width. Notice that A here, which stands for an area, is dependent on the values of two other quantities, length and width. So area here varies directly with its length and width. In general, a joint variation is expressed as y equals k x z, where k is the constant of variation or proportionality constant. It cannot be equal to 0. And to solve for k here, we are going to divide both sides by xz. So this will become k is equal to y divided by xz. Let us translate the following into an equation. The force F applied to an object varies jointly as the mass m and the acceleration a. So we have F equals k m times a. Number 2, the area of a rectangle is jointly proportional to its length and width. This is our example earlier. A is equal to K LW. Next one, the voltage V varies jointly as the current I and the resistance R. So we have V equals K times I R. Next one, the volume of a right rectangular pyramid varies jointly with the area of the base and the height. So we have V equals K times B times H. And the last one, the volume of a right cylinder varies jointly as the square of the radius and its height. So we have V equals K R is squared times H. Now, let us solve. Y varies jointly as x and z, and z is equal to 3 when x is equal to 10 and y is equal to 30. Find y when x is equal to 15 and z is equal to 6. So first, we are going to construct our variation equation. Y varies jointly as x and z. This will be y equals k xz. To solve for the value of k, we are going to divide both sides by xz. This xz here will cancel out, leaving us k. So k is equal to y over xz. Now we are going to substitute the values that we have here. Y is equal to 30, x is equal to 10, and z is equal to 3. 10 times 3 is 30, and 30 divided by 30 is 1. So our k is equal to 1. Let us rewrite once again our equation, and let us substitute this time x is equal to 15, z is equal to 6, while our k is equal to 1. 1 times 15 is 15, and 15 times 6 is 90. So y is equal to 90. Let us try this. The volume of a right rectangular pyramid varies jointly with the area of the base and the height with a constant of variation of 1/3. So we are given here the value of k. Find the height if the volume is 150 cubic units and the area of the base is 90 square units. Let us construct first our variation equation. So volume varies jointly. So V is equal to K, area of the base times the height. So we have V equals 1/3 base times the height. Now let us substitute the values that we have here. We have the volume is 150, our base is 90, and we are looking for the height. 90 divided by 3 is 30. To solve for h here, we're going to divide both sides by 30. So 30 here will cancel out, leaving us h, and 150 divided by 30 is 5. So h is equal to 5 units. Let us do extra challenge. The volume of a right circular cylinder varies jointly as the height and the square of its radius. The volume of a cylindrical tank whose height is 8 meters and radius of 3 meters is 72 pi cubic meters. If you need a cylindrical tank with a volume of 300 pi cubic meters, what must be the height if its radius is 5 meters? Let us construct first our variation equation. So we have here the volume, so that would be V, varies jointly equals K, height and the square of its radius. So we have V is equal to K, H r squared is square of the radius. Let us substitute our values here. The volume is 72 pi, our h is 8 meters, and our r is 3 meters. 3 squared is equal to 9. 8 times 9 is 72, so we have 72k here. To solve for k, let us divide both sides by 72. This 72 will cancel out, and also this 72. So we have k is equal to pi. Now let us rewrite once again our working equation. This time we have the value of k, that is pi. Our h is what we are looking for. R is 5 meters, and the volume is 300 pi. Let us substitute those. 5 squared is 25. To solve for h, we're going to divide both sides by pi 25 or 25 pi. So pi here will cancel out. Same with the pi here and the 25, leaving us h. And 300 divided by 25 is 12. So h is equal to 12 meters. For the summary, here are the things that we discussed in this lesson. Take time to understand this. Now, it is time to check your understanding. Pause this video for more time. Let us answer. Z varies jointly as x and y. Also, z is equal to 60 when x is equal to 5 and y is equal to 6. Solve for y when z is 100 and x is equal to 10. Let us write first our variation equation. Z varies jointly, so z is equal to k, x, y. Now we're going to substitute the values that we have here. Our z is equal to 60, our x is 5, and our y is 6. 5 times 6 is equal to 30, and to solve for k, we're going to divide both sides by 30. 30 here will cancel out. So k is equal to 60 divided by 30 is 2. K is equal to 2. Now let us rewrite once again our equation. This time we know already the value of k, and that is 2. Our z is 100 and our x is equal to 10. Let us substitute those. 2 times 10 is 20. To solve for y here, we're going to divide both sides by 20. So 20 and 20 will cancel out. Y is equal to 100 divided by 20 is 5. So y is equal to 5. Let me know if you got it correct. Gets? Our next lesson is combined variation.